Here's another centripetal force problem. This time we have a car, my funny looking little Herbie the Love Bug car here, coming out at you. There's some center of the turn. The car is going like this, around in a circle, on a banked surface where there is no friction. So all that's keeping the car on the track is the fact that the curve is banked. So if I want to equalize the forces, I'm asking myself, in the direction of motion, which is this way, what provides this piece of the centripetal force, which is mv squared over r cosine of theta? What provides it? Gravity, the part of gravity that acts down the plane, which is mg sine of theta. So by equating these two, once again, I find that mass is unimportant when you are in a banked curve. Again, they don't ask how much the car weighs. On a racetrack, it doesn't matter what equipment a stock car carries. If the curve is banked, it will stay in the banked curve regardless of its mass. It'll have the same slipping if there was no friction. I've done the first case where it was a level road with friction. Now I'm doing a banked curve with no friction. Booby prize for you if you guess that the last example will be a banked curve with friction. And that's a real vector nightmare. So again, it's one of the equations you might want to memorize rather than have to derive it during the test. So I canceled the masses, and please remember that sine divided by cosine is what? Tangent of theta. So solving for the velocity, v squared equals rg sine over cosine is tangent of the bank angle theta, and the velocity is the square root of rg tan theta. Notice that tan theta plays the same role that mu played, the coefficient of friction, on a flat surface. So there's still something that helps keep us in the turn. And then in the case of a banked turn with no friction, it's the tangent of theta. And we know that this makes sense to us when we think about drawing a banked curve and putting an object on it that is just in balance. So if we had a banked curve, a banked plank here with a mass on it m, and we have mg and times the, remember this is the sine of theta, and the friction force holding it in place is mu mg cosine theta. And remember we asked a question about whether a box would slide, and we said it will slide if mg sine of theta is greater than or equal to mu mg cosine theta. So we whacked those out, and it will slide if mu was less than or equal to the tangent of theta. So it should come as no surprise to you that in some sense tangent of theta and mu are related on an inclined plane. So that's sort of the quick and dirty proof that on an inclined plane, considering centripetal force provided by gravity alone, or the component of gravity in the direction of motion, not straight down, again, normal force and then parallel force, that we find that the velocity is related to the square root of the tangent of theta. In the level Lazy Susan case of spinning, we found that the velocity was the square root, again, of rg, but instead of tangent of theta on a flat surface, it was mu. So those two examples together can be combined to do the grand banked curve with friction, which we will do shortly.